All right, example 4. Let's do this integration again, and I'll let you see it now with a different equation. So I'm going to come up here and change my equation. Now instead of x squared, we'll do x cubed, and I'm going to make that out all the way out to 1. And let me resize this so you can see the picture. All right, here's the right Riemann sum. I don't know if I said that. When you find the definite integral, it uses the right Riemann sum. So there's the right Riemann sum. And I can probably adjust this just a little bit to make it easier to see what's going on. Let's go from -5 to say +6. There we go. There's our right Riemann sum. And we can see this is an overestimate. These boxes would be shaded too wide. Well, if I wanted, and let me make sure I'm looking, we want to find the area between 2 and 4 only. So we're only looking between 2 and 4 on this problem. So I'm going to come over here and change my problem where I'm only looking, I need to go to this A list from 2 to 4. And this B would need to be now, let's make that a 3. That needs to be a 3. And this a 2. Okay, so I might need to correct a few things. Hang on one second. Okay, so I had to just fix a little programming. So we're looking for the area now just between these two values. So we're not just going to search that. I need to unshade that. Hang on one more second. There we go. So we're looking for the area in between here. And so the idea is this. What would be if we shrunk the Riemann sums as small as possible? What would be the area for that part? And what we could do here is just go to our integral, and to be fast, I'm going to just change that to a 3, and we should have the area as being 62 units squared. 62 units squared. Again, what happens there is instead of taking, so like the very first example one, we did right Riemann sums from the right endpoints. Instead of taking the right Riemann sums, which this would be an overestimate, you could do this and find the right Riemann sum. And you would be adding up the values from 2 to 4, which would be 9. Oh, wait, I did it by halves there. So here I would need to do it by halves. If I wanted to do this math right, let me change this to, and I want to go from 2, 2.5, 3, 3.5, and 4. Okay, and so these would be my areas if I was doing the right Riemann sums, starting actually at 2.5. So that would be this area right in here would be like 8.3125. This area right there would be the 14. This area is the 21.9375. Oops, 9375. And finally, this area right in there would be 32.5. And if you added those up, you'd see that that is an overestimate that is greater than the 62. And so that, I'm just trying to show you the difference of what's happening. That would be looking at this Riemann sum. Well, counting by halves. This is counting by ones. But let me go to half, 2.5. There we go. That's the area shown there. On these blocks, it would look like that. But the actual integral, what it does is it shrinks these infinitely small to get a more accurate representation. So with that, you go ahead and try to see if you can find the area for this particular problem here, y equals 2x cubed plus 3, the area under that curve, and the x-axis from the interval 1 to 3.